Alright guys, welcome back. So in this video here we'll be talking about testing claim regarding a population mean. In lesson 6.4, when we first introduced the distribution of sample means, we note that it was approximately normal given the fact that if the sample size is large enough and the mean of all the sample means is equal to the population mean, and then the standard deviation of the sample means is equal to population standard deviation divided by square root of n. And these results were part of the central limit theorem. So we have this here, z equal to x bar minus mu over sigma divided by square root of n follows a normal distribution. One thing we also know that is that it said that it is unreasonable to expect to know the population standard deviation without knowing the population mean. So this problem was solved by William Gossett when he established the t distribution. By looking at a small sample size, he was able to determine that the variable t equal to x bar minus mu over sigma over standard deviation divided by square root of n. That has a t distribution with degree of freedom n minus 1. So we use that t distribution when we discuss inferential statistics method confidence interval estimate. So we are going to use the same distribution in this lesson when we do the hypothesis testing regarding a population mean. So we're going to go with the situation where we don't know the population standard deviation, so we're gonna have to use the sample standard deviation. So as a result, that it forms a t distribution. So there's a several requirements when we do this. We're not gonna focus too much on the requirements, but usually in this class or in this textbook here, any sample drawn usually given is a simple random sample, and we're gonna assume that the population is normally distributed. If not, we want to check if the sample size is greater than 30. And so from the central limit theorem, if sample size is greater than 30 or large enough, this implies that the distribution of x bar with that sample size is approximately normal. So we're not going to emphasize a lot on the requirements. And it says here, if n is less than 30, we use normal quantile plot to show if the sample is indeed come from the normal distribution, which approximately normal. This is a lesson that we skip. But before we get to example, there's a few notation I want to review, and also the test statistic formula that we want to go over before we get to example. As far as notation goes, we know that sample n is always stand for the sample size. All right, that's what n stands for. S is sample standard deviation. Okay, x bar is sample means, and then mu sub x bar. This notation stands for the mean of all sample means. So this is the population parameter. And from lesson 6.4, we also discussed that the result of this mean of all sample means actually equals to the population mean, according to the central limit theorem, right? So that's what we discussed in lesson 6.4. So that's what we're going to use, as part of a math formula in terms of carry out the hypothesis testing for a mean. So the formula we're using for the test statistics in this lesson is the t test statistics is going to be equal to x bar minus mu over sample standard deviation divided by square root of n, and mu is the population parameter, or sometimes this is the value that we use from usually it comes from the claim value. So someone will claim the mean of something, some sort of distribution will equal to this number, and then we're gonna use that number as part of or assumption to carry out the test and to show whether the sample is significant or not. So usually that's the claim value. Okay. So that's the test statistic formula for testing a claim regarding a mean. And recall from 6.4, even chapter 7, when we use a t-distribution for a small sample size, we also those t-distribution depends on the sample size. So because of that, we have this thing called degrees of freedom, and that was df here. The degree of freedom is still the same, n minus 1. So to find the p-value for certain test statistics, we usually use technology or use a t-distribution. Technology is much easier. T-distribution a little bit confusing. I can show both method when we get to example. And if we don't like the p-value approach, we could also use the critical value approach, and I discussed that in the previous lesson as well. When we use the critical value approach, a given significant level, we can determine the t critical value that separate the significant level from the non-significant level, region, and that's still using the same degree of freedom. As far as writing the conclusion for hypothesis testing regarding a mean, we still have the same condition, and that is you have one or two things. So we look at first we assume. So usually we always, let me go ahead and just erase this real quick. Usually we always assume, we start out saying that assume that the no is true, right? So it's true means equal to some claim value. From that claim value, we look at the distribution, and then look at we draw a sample from that distribution, and then we want to see whether that sample is significant or not. So that to show that, we look at the p-value. So if the p-value is not significant, meaning it's greater than the significant level, which is alpha. So if this is the case, then we fail to reject the null hypothesis in favor the alternative, right? So that's the first conclusion there. The second conclusion, if we assume the null hypothesis is true, and we look at that distribution, draw a random sample, and that random sample is indeed significant. So if it's significant, then the probability of obtaining such sample is much less than the significant level alpha. If this is the case, then we're saying that, okay, we don't support the null hypothesis. We're going to go ahead and reject that assumption, and we're going to favor, we're going to favor the null hypothesis. And it turns out that it's either, one of these two is going to be the claim. Either the null or the alternative is going to be a claim. So, at the end, of this conclusion here, we're just going to say, well, write a sentence. Usually at this point, we're going to write a sentence, to address the original claim. Okay. And that original claim can be part of this statement or that statement. So it depends what we end up supporting. If we, if the claim is actually the null hypothesis and we support the null, then in that case we support the claim. If the claim is the alternative and we end up not supporting the alternative, then we don't support the claim. So it depends how the conclusion turns out based on the evidence. Okay. So I'm gonna go ahead and pause this video, and I'm going to start the next video on exercise 1 regarding cell phone radiation. So it turns out that cell phone has certain level of radiations. It's called SAR, specific absorption rate. And these cell phones are old here, but it's just a small sample here. So I'm going to start the next video in this example and discuss the claim in this problem.